So, next we shall be starting with logic gates. So, gates are used for realizing digital circuits. Now, before we do that, we will just clear one confusion which was there regarding this. So, there was a confusion in Boolean algebra, where we had an expression like a plus a bar b, and which we wanted to equate to a plus b. So, that simplification process there was some problem. So, we do the simplification like this, like a plus a bar b, it can be written as a dot 1 plus a bar b, where this 1 can be written as a into 1 plus b plus a bar b. So, if you multiply, you get a plus a b plus a bar b, and so it gives a plus a bar and b. So, this a plus a bar is again 1. So, this gives a plus b. So, in one class there was some confusion about it. So, this is the derivation. So, with this we will be starting with this logic gates. So, as I said that logic gates are circuit elements, digital circuit elements, by which we can realize the digital circuits. So far we have seen how to minimize the Boolean function, and this class onwards we will see how to realize a Boolean function in terms of components. So, if you the binary quantities and variables. So, if you look into a binary quantity is one that can take only two states. So, either it is high or low. If you can think of it as if there is a battery and there is a switch and a lamp, and then when this switch is closed, then only the lamp will glow. So, this switch has got two positions, open position when it is now like this, and the closed position when this bar connects to this point. So, that way we have got two positions for the switch, open position and closed position. So, when this is open, then the lamp does not get the current flow. So, lamp is off, and when this is closed, the lamp is on. So, that way we can think of it as a variable. The switch can be considered as a variable that has got two states in it, open and closed, and accordingly the lamp has got two states, off and on. So, this S and L, that is switch and lamp, both are binary quantities or binary variables. You can just represent in the form of a truth table, where we say that this open is represented by 0 and closed is represented by 1 for the switch. So, switch can be either at state 0 or at state 1. On the other hand, the lamp, it can be off, which is represented by say 0, and on, which is say represented by 1. You see that these open represented by 0 or this on represented by 1. So, these are arbitrary. So, this is done by the designer. Okay. So, for the design simplicity, so you can follow any of the logic. However, one thing is true, that whatever convention we follow, so that has to be followed uniformly. So, you cannot change from one part of implementation to another part while doing this thing. So, if we consider two switches, like this, suppose I have got S1 and S2, two switches, they are connected in series. So, S1 can be either open or closed, and S2 can also be open or closed. Now, this lamp, it gets the current flow only when both S1 and S2 are in closed state. Okay. So, if I represent 0 open by 0 and closed by 1. So, only when both the switches S1 and S2 are closed. So, they are getting the value 1 and 1, then only the lamp is on. So, this L equal to 1, otherwise the lamp is 0. So, this is actually the condition, that the lamp gets on only when both S1 and S2 are on or both are closed. So, this S1 and S2. So, please mind this term AND. So, this AND gate is coming into picture. So, here I say that L, the logic expression for L is given by S1 and S2. So, when S1 and S2 both these variables get the value 1, then only L will get the value 1, otherwise L will get the value 0. So, this is the AND operation of S1 and S2. Similarly, we can connect the two switches in parallel. So, apparently it seems, why should we connect two switches in parallel, but for the sake of example. So, let us take it like this, that we have got two switches connected in parallel, S1 and S2, and either of the switches being closed, the light gets, the lamp L gets current, as a result it turns on. So, we can say that if again the same thing, if 0 for switches represent they are open and 1 represent they are closed. So, whenever either S1 or S2 is 1, then L value becomes equal to 1. So, this is the truth table, and here the operation that we are doing, say L is on if S1 is 1 or S2 is 1. So, again mind this term OR, because this is the OR operation of two binary quantity. So, this L binary quantity or binary variable L, it gets the value of S1 and S2, S1 or S2, where S1 and S2 are the again two binary variables. You can connect three switches in series like S1, S2, S3. So, what happens is that here this lamp L gets current only when all the three switches are closed. So, this can be represented in the form of a truth table, where this S1, S2, S3. So, if I just write down all the possibilities. So, S1, S2, S3, these are three variables. So, it can start from 0, 0, 0, 0, 0, 1 and go up to 1, 1, 1, where 0 means the switch is open and 1 means the switch is closed. So, as I said that since this is a series switch S1, S2, S3. So, this L will be equal to 1 only when S1, S2, S3 all of them are equal to 1. So, in the truth table also you see that this L equal to 1 only when S1, S2, S3 all are equal to 1. Similarly, we can have OR operation. So, we can have in parallel, the switches may be connected in parallel, S1, S2, S3 they are connected in parallel. So, whenever any of these switches are closed, the lamp is turned on, and when all the switches are open, then the lamp is off. So, whenever this lamp L equal to 0 only when S1, S2, S3 all of them are equal to 0. Otherwise, whenever any of them is equal to 1, the L value is equal to 1. So, we can say that as if this lamp L is equal to S1 or S2 or S3. So, it is the OR of three variables. Okay. Three, all the S1, S2, S3 three variables are ORed to get the value of L, but OR so far whatever we have seen. So, OR is a two variable operand, okay, it is a two variable operation or two operand operation. So, we have to write two ORs in between. So, S1 or S2 or S3. Okay. So, this way we can represent three switches in parallel, slightly more complicated one. So, let us say that we have got the switch S1 connected in series with a parallel combination of S2 and S3. So, for this lamp to glow, S1 must be closed and at least one of the S2 and S3 should be closed. So, this is basically S2 or S3 and S1. Okay. So, that is the logic for L. So, here also if you look into the truth table, this L is on. For L to be on, S1 must be equal to 1 and at least one of S2 and S3 should be equal to 1. So, then only L is equal to 1. So, this overall operation of this lamp can be written as L equal to S1 and S2 or S3. So, that captures the status of all the three switches S1, S2, S3 and we get the combination. Okay. So, this way we can represent this operation on Boolean quantities by means of switches and some output. So, now if we suppose we have got an unknown network. Okay. So, this is a black box. So, this is a black box, I do not know what type of connection we have between these points. So, we say from this output of S1, how is it connected to S2? So, S2, S3 may be connected in series, may be connected in parallel, maybe all of them are in parallel or maybe all of them are in series. So, there may be many possibilities. So, it may be the connection pattern is like this, that from this point, from this point we have got so from this point we have got a connection that takes it to this as well as this, and then from this and this they are connected to the output point. So, what happens is that, so we are getting S2 or S3 because S1 has to be closed and then at least S2 or S3 has to be closed. So, that we can get that, so that we can reach this point. Okay. So, this way, or it may be that we have got a connection like this, that S1 is connected like this and S2 is S2 to S3 it is connected like this and this is the connection. So, that way what we have is that S1, S2, S3 they are connected in series. Okay. So, this is AND operation. So, if this is an unknown network, then we can we may try to represent. So, in a black box form, so we can say that as if there are 3 inputs S1, S2, S3 for this black box and there is one output L. Now, how do we find out the operation? So, exact operation. So, for that what we need to do is that we need to apply different combinations and see whether the light glows there or not. Suppose only when we connect S1, S2, S3 all of them in closed position, then only the light glows. That means, only when S1, S2, S3 all the variables are 1, L will be equal to 1. So, it is a AND of 3 variables. So, that way you can identify the logic function that is implemented by this box by applying different switch combinations here and checking the status of this light. So, this logic gate, so they are building blocks for creating digital circuits and there are 3 elementary logic gates and a range of other simple gates. So, we will see that there are 3 basic gates and from there are many other derived gates. Each gate has its own logic symbol which is universally accepted. So, it is expected that we use those symbols to represent those logic gates. And so, you can represent, so since each of them is a symbol, so you can use those symbol for AND operation, OR operation, etc., and then connect between the lines by means of some lines, connect between the inputs and outputs by means of lines to get the overall logic diagram. So, that we will call a logic diagram. So, the complex function can be represented by logic diagram and the function of each gate can be represented by a truth table or using the Boolean notation. So, you can either use a truth table or a Boolean notation in terms of some Boolean function. So, you can represent it. So, we will start with the first basic logic gate which is the AND gate. So, this is the symbol of the AND gate. Okay. So, this is universally accepted. So, it is expected that whenever we are drawing AND gate we use this symbol. Now, why this symbol? There is no reason like that, and in some special cases you may use some other notations, but it is expected that in general you use this notation. So, this is the symbol. So, whenever in the digital circuit you see this symbol, we understand that it is an AND gate. Now, there are 2 inputs coming to it and 1 output going out of it. So, AND gate always has got 1 output, but the number of inputs may be more. So, in this particular example, so we have got 2 input AND gate. So, if there are more number of inputs, so more number of lines will be connected to input side. So, this is the input side, this is the output side. So, if there are more number of inputs, so they will be connected to the more number of lines in the input side. So, this same circuit symbol, so it can be represented in the form of truth table. So, truth table actually tells what is the functionality implemented by the corresponding logic element. So, as the name suggests, this is an AND gate. So, only when both the inputs A and B are equal to 1, we will be having output C equal to 1. So, 0 0 when the inputs are 0 and 0, output is 0. 0 1 then also 0, 1 0 then also 0 and 1 1 is 1. So, this is the truth table and the in terms of Boolean expression. So, this is an AND of A and B, 2 variables. So, C equal to A and B. So, in different situations, so we will be using different notation, like when you are trying to represent the circuit, we will draw this type of gates, this type of circuit symbols. When we are interested about the functionality in the form of some truth table, so we can write it like this, detailed functionality. Sometimes we need a compact notation, so there we will be writing in terms of the Boolean expression. So, depending upon our requirement, we will do that. The next fundamental gate that we have in digital circuit is the OR gate, and again this symbol is the universally accepted symbol, and it is again expected that for OR gate we will represent it like this. So, this is the circuit symbol, this is the truth table. So, OR means whenever at least one of the inputs is equal to 1, output will be equal to 1. So, this is happening here. So, you see whenever A or B at least one of them is equal to 1, output C is equal to 1. So, we get C equal to A plus B. So, this is the Boolean expression and this is the truth table. Again the same thing, that this is a 2 input OR gate. So, if you want more number of inputs, so they can be added here. So, theoretically there is no limit on the number of inputs that you can have to a gate, but of course, ultimately these will be represented by digital ICs. So, they will have their own restrictions. So, and you will find different number of inputs for different IC chips. So, you can have say 2 input OR gate or 4 input OR gate like that. So, normally we do not have or do not have odd number of inputs to the gate, and 2 and 4 these are the common ones. So, we do not have more because that will make the gate more complex. Another fundamental gate that is there is the NOT gate or the inverter. So, its symbol is like this, a triangle, and on top of that there is a bubble. Okay. So, this is a single input. So, or NOT gate cannot have more than one input. So, it has got a single input and it has got a single output. So, as the name suggests, so this is the invert of the input, output is the invert of the input. So, in terms of truth table, whenever A is 0, B is equal to 1, and whenever A is 1, B is equal to 0. And in terms of Boolean expression, it is written as B equal to A bar. Okay. So, this A bar, so this is the complement of A. So, that is the NOT gate. Okay. So, sometimes we use a logic or buffer gate. So, this is buffer means that it just copies the input to the output. So, whenever A is 0, B is also 0, whenever A is 1, B is also 1. The logic Boolean expression is B equal to A. Apparently, it seems that why do we need such buffer gates? Okay. So, sometimes what happens is that we need to drive some large load in terms of the circuit, in terms of circuit elements, like maybe it may so happen that one gate output it drives a number of gate inputs in the next stage. So, that way it has to drive a large current, and these buffers they have the capacity to drive large current. Okay. So, they can be connected. So, that way we can use this type of buffers. Okay. So, this otherwise as far as logic is concerned, it does not add anything to the circuit. So, it just copies the input to the output. Next we come to some derived gates like the NAND gate. The first one is a NAND gate. So, this is actually you can say that NAND is equal to AND plus inverter. Okay. So, so this AND plus inverter, you see that here the symbol is also like that. So, this is the AND gate, and after that there is an inverter bubble. Okay. So, this AB, so as the name suggests, so this will be output will be equal to 1. Okay. Whenever the AND gate output will be 0. So, AND gate output is 0 whenever any of these inputs is equal to 0. So, in terms of NAND gate, we can say that whenever any of the inputs is 0, output will be equal to 1, and only when both the inputs are equal to 1, the output will be equal to 0. So, this is the truth table. So, you see that whenever when both the inputs are equal to 1, output is equal to 0, otherwise output is equal to 1. So, symbolically, so or in a Boolean expression, so it is represented like this, C equal to A B bar. Okay. So, this is also written as this dot is often ignored. So, we write it like this. So, A B bar. Okay. So, this is also there. So, this NAND gate, so you see that NAND gate is called a derived gate because it can be derived from the AND gate and inverter. So, AND or inverter, they are fundamental gates, and from them we can derive these gates. So, NAND gate is one such derivation. Next we will look into NOR gate. So, just like NAND gate was equal to AND plus NOT. So, similarly, if you do OR plus NOT, what you get is a NOR gate. So, what we have got this NOR equal to this NOR is equal to, so OR plus inverter. So, OR plus inverter, and the symbol is also like that. So, we have got here the OR, and then there is an inverting bubble. So, OR plus inverting bubble. So, that is the circuit symbol for NOR. Of course, the other things remain same, like I can have more number of inputs here and all, and then the truth table is simple, like the OR gate was whenever any of the inputs is equal to 1, output was equal to 1. So, since this is NOR, so whenever any of the inputs is equal to 1, output will be equal to 0, and only when both the inputs are equal to 0, this NOR gate output is equal to 1. So, this is the C equal to A plus B bar. So, that is A plus B whole bar. So, that is the Boolean expression for NOR. Okay. So, of course, you can apply De Morgan's laws on this to simplify the circuit, that we will see later. So, next we will look into the another derived gate, which is known as exclusive OR gate. So, if you if you remember the OR gate, so it was like this. So, the truth table for OR gate was the A, B and C. So, whenever any of the inputs was equal to 1, so this was equal to 1. So, 1 0 is also 1, and 1 1 was also equal to 1. So, this was the truth table for OR gate. Now, you see that in case of XOR gate, we first compare at the truth table level. So, truth table wise you see that when both the inputs are equal to 1, XOR gates gives output 0, whereas OR gate gives the output 1. So, as the name suggests, this exclusive OR gate, it requires that exclusively only one of the inputs will be equal to 1. So, if both the inputs are equal to 1, then the output will be equal to 0. And as a result, this OR function, so this is also sometimes called inclusive OR. So, this is also called inclusive OR, just to separate it out from exclusive OR. So, this is also known as inclusive OR. So, sometimes we will see that exclusive OR gate in detail later. It has got many fundamental usage in digital circuit design, and you see that here what we are having? We are having two inputs A, B, and this C is output, and C can be written as this is the symbol for XOR. So, this plus is the symbol for OR, and if you put a circle around it, so this will be an XOR operation. So, this is an XOR operation. So, this is if both the inputs are equal to 1, then the output will be 0, output is 1 only when exactly one of the inputs is equal to 1. So, next we will look into the inverted version of XOR, which is known as XNOR gate, exclusive NOR gate. So, this is NOR, but exclusive. So, NOR gate was that whenever we have got any of the inputs equal to 1, output was equal to 0. So, this is the difference. In XNOR gate, when both the inputs are equal to 1, so output is equal to 1. So, this is not equal to 0. So, in a NOR gate, this output is equal to 0, but in an exclusive NOR gate, so this output is equal to 1. So, for for NOR operation, so the truth table was like this. So, this was the NOR operation, where when both the inputs are equal to 1, output was equal to 0, now it will be equal to 1. So, symbolically we represent it as C equal to A XOR B whole bar, or it is written, it is read as A XNOR B. Okay, so, it is read as A XNOR B. Next, we will look into some design of this combinational logic. So, using these basic gates that we have discussed so far, so we can realize some combinational function. Any digital circuit can be represented by in terms of these gates. So, we will slowly go towards that. Now, if you look into all digital systems, so they can broadly be classified into two categories. One is known as combinational logic, another is known as sequential logic. Combinational logic is like this. So, output is determined solely by the current states of input. So, if I represent the if I represent this this is suppose is a digital circuit. Suppose this is a digital circuit. Now, it has got a number of inputs, say A, B, C, and it has got say two outputs P and Q. Now, if it happens like this, that the values of at any point of time, the values of P and Q, it is dependent on the values of A, B, C at current instant only. Okay. So, it does not depend on the previous values of A, B, C. If that is the situation, then we will tell that this is a combinational circuit, because it does not depend on the history of the inputs in previous times. On the other hand, there will be another class of circuits where you will see that this output P and Q, it will depend not only on the current value of A, B, C, but on the previous values of A, B, C also. Like if you observe the system from time t equal to 0 and at present you are at time say t equal to 10, then the output P Q at time 10 will be dependent not only on the values of A, B, C at time 10, but also on the values of A, B, C at time instants 9, 8, 7, 6 up till 0. So, at all the previous values of A, B, C. Okay. So, it need not be exactly at this boundaries like 9, 8, 7. So, you can say that it depends on the total history of these inputs at from the beginning of the system. So, that type of logic will be known as sequential logic. So, in our course we will be dealing with both the types of logic. So, both combinational and sequential, but initially we will be discussing on combinational logic because that is simpler to understand, and then we will proceed towards the sequential logic. So, suppose we have got a Boolean expression x equal to a plus b c bar. Okay. So, to how can we realize in terms of logic gates? So, you see that this OR, so find at the highest level we have got this OR operation. Okay. So, so at the topmost level, so we will have this OR gate. So, OR gate will have two inputs. So, this A input and this B C bar input. So, A input is connected to first input of OR gate, and this B C bar has to be connected to the second input of OR gate. Now, how do you get B C bar? For getting B C bar, so you have to do B and C bar. So, you need an AND gate. So, where one input is B, another input has to be C bar. So, this here you get B C bar. Now, how do you, so B we have already got because B is a primary input to the circuit, and then this C bar, to get C bar, what we do is we start with C, put an inverter on here, and then from this C we get a C bar. So, that way this circuit, so it represents it can implement the Boolean expression A plus B C bar. So, this way these Boolean expressions are implemented. Like let us say take another example slightly more complex, y equal to a bar b plus c d bar whole bar. Okay. So, you see that this, if you look into the highest level, so this is a NOR operation. So, this plus, so this is OR and there is a inversion at the top. Okay. So, that means this is a NOR operation. So, I take a NOR gate, and then to the NOR gate I should have the inputs a bar b and c d bar. So, this NOR gate, it is getting two lines. So, in one line I have to realize a bar b, another line I have to realize c d bar. Now, how do I realize a bar b? For getting a bar b, I have to do AND of a bar and b. Okay. So, this is a AND gate and we have got a bar and b here. So, b is coming directly from the primary input, but to get a bar I have to take an inverter, and then this a will be applied here and a bar will be obtained from there. Similarly, for getting C D bar, so I need another AND gate, and in this AND gate C will be one of the input and D bar will be the other input, and for getting D bar from D I have to have an inverter in between. So, this way starting from the top level of your expression, so you can just go back realizing till the simplest element, that is till you reach the primary input. So, till the expression refines to the primary input, we have to go on doing this thing. So, we can also do something for generating the Boolean expression from a logic diagram. So, suppose this is a Boolean, this is a logic diagram. So, we can trace through this logic diagram to see how the corresponding Boolean expression can be derived.